Okay, so you know how to do integration. You've had calculus 1 and 2. You're very knowledgeable. And you know that when you compute an integral, a definite integral, you are finding the area uh, underneath the curve. Well, you're finding the area between the function, f of x, and the x-axis. And that area could be positive area, that area could be negative area. Well, when we talk about double integrals over rectangles, we are not finding area, but we are computing volume. We are finding the volume underneath a function of x and y. A function of x and y is a surface, right, in three-dimensional space. So if you want to find the volume between the surface and the xy plane over a rectangular region, you would use a double integral. Now the question is, how do these double integrals work? How do they work? Well, just like in calculus 1, before we get to double integrals, okay, we need to understand it'll help us to work with Riemann sums. So, like for instance, and the book actually mentions this. They actually say, you know, here's the Riemann sum, and you know what that Riemann sum was used for in that box 1 there. That Riemann sum was used to approximate the area under the area between a function and the x-axis. And if we take that Riemann sum, okay, and we make the subintervals, let them get smaller and smaller, we end up with an integral. So this is calculus 1, calculus 2. But what about double integrals? How do we interpret a double integral? Well, for that, okay, we'll go here to figure 2. And in figure 2, you see a function of x and y and over a region R. Now, what are the x limits for that region R? What are the x limits? What values do they go from? Good, that's right, you knew that, silly. A to B. What about these y limits? Okay, they're x limits and y limits. They go from C to D. Okay, so how would we estimate the volume underneath this surface over that region R in the xy plane? How would we do that? Well, what we can do, okay, without getting too technical, is we could take the region and divide it into sub-rectangles, all of equal size, a delta x. They all have width delta x and height delta y. Okay, you see that in the picture there. And we could pick points in each of the rectangles and compute the function at each of those black points. Now, the value of the function would be the value, it would be the height of the surface at that point, right? If we compute f of xy for each of those black points there in the sub-rectangles there, we would be computing function values. They would be heights. So you see, what you can do is you can think of, well, here's figure 4. Here's figure 4. It shows it pretty nicely. So there you have a subrectangle in the xy plane in that region D or region R, and the area of the rectangle is called delta A. So you see above the picture there in figure 4, there's a delta A. Okay, and For a point in the subrectangle, you compute a point x sub ij, y sub ij. You need two indexes now, I and j, because the points can be moved horizontally and vertically, right? So that you need to do that so that you get a point, select a point in every subrectangle. But the function value of x sub ij, y sub ij, if you take that and you multiply by delta A, as you see above there, what's that going to give you approximately? What would that give you? That would give you a piece of, well, let me ask you this. Do you see in figure 4 a box? They've drawn it in with dashes, but you see like the blue dashes there outline a box? Yeah, that's right, and it's a box, and the function value times delta A would give you what of that box? The function value gives you the height. Delta A would be an area. If you take height times area, what do you get? You get volume. Good. Good, Hunu. Good, Ellie. You get volume. And so that's that function value times delta A that you see above the picture. That's the volume of the box. The box shown in figure 4 above that subrectangle, R sub ij. And the volume of the box approximates the volume underneath the surface, or between the surface and the xy plane over that subrectangle. So if we wanted to find the volume, if we wanted to approximate the volume between that surface and the xy plane over that region R, the full region R, we would just add up. We would add up all the volumes of the boxes, and we would get a double Riemann sum. A double Riemann sum. Now, as you let the subrectangles get smaller and smaller, would this approximation for the volume get better or worse? If you make the subrectangle smaller, it'll get better. It'll get better, absolutely. And so this volume here, then, if you take the limit, that means if you let m and n go to infinity, you're going to get the actual volume. The actual volume. And this limit is going to turn into a double integral, right? It's going to turn into a double integral. So, and by the way, there's a picture. There's a picture where they have, you know, a bunch of boxes, okay? But this volume here is going to be, this limit as m and n goes to infinity is going to give you the true volume between that surface and the xy plane. And so that's the definition of the double integral. That's the definition. Okay, that's, and you can see that definition is analogous to a single integral. Okay, the limit of a Riemann sum gives you a single integral. The limit of a double Riemann sum gives you a double integral. Okay, are there any questions on that? All right, well, let's look at a few examples. Let's look at a few examples. So if we go to example 1, okay, and maybe let me just remove the highlight here and put it back so you know what we're doing. So in example 1 from section 12.1, they want you to estimate the volume of the solid that lies above that square. So that notation means that x goes from 0 to 2 and y goes from 0 to 2. The first two numbers, 0 to 2, stands for the x values. The second two numbers, 0 to 2, stand for the y values. So we want the volume of the solid that lies above the square and below the elliptic paraboloid. Okay, we want to estimate the volume. Now, does that elliptic paraboloid, z equals 16 minus x squared minus 2y squared, does that paraboloid go up or down? It goes down. Good. What's the highest value? What's the highest value of that paraboloid? Good, 16. So this is, in terms of a picture, this is what, well, there's figure 6, where, so what we want to do, hold on though. Now what they say is, well, you know, you haven't learned how to do a double integral yet, so we're going to approximate the volume. So let's divide that square region into 4 equal squares and choose sample points to be the upper right corner of each square. Okay, so, all right, what would that look like? Well, here's figure 6. Okay, there's the region in yellow there, or I guess that's, well, yellowish. I'll call it yellow. And you see they have 4 regions. And, well, Ian, what happens is you'll be told in your homework for section 12.1, you'll be told what points to use. Okay, you'll be told. And, you know, it's going to be kept pretty simple. But it's important that you experience these kind of problems so you have a feel then for the double integral. But you see there, for every subrectangle, R11, R12, R22, R21, they pick a point in the top right corner. And then what they're going to do is they're going to let those points, they're going to use the function at those top right corners to define then how high the box is. You know, they're going to evaluate the function at those top right corners, and those function values will define how high the boxes are. And now you have to find the volumes of the boxes and add them, but to approximate the volume. But are there any questions on figure 7? Okay, okay. So above here, here's how they approximate the volume. So the points are 1, 1, the corners. Well, let me actually go back to the figure here. So the corners are 1, 1, 1, 2, 2, 1, and 2, 2. Those are the upper right corners of each subrectangle. So to approximate the volume then, here's how you would do your approximation. So, and the area of each subrectangle has area 1. Okay, so maybe maybe what I can do is try to have them both show here. No, wait. Cancel that. I really just want to highlight it. I don't know if it'll let me. There we go. That'll work. So now, are there any questions? They get an approximate volume of 34. Are there any questions on how they got that volume? Who's feeling good? Who's feeling good so far? All right, good Ellie, good Ian, good Juliana. Are there any questions? Okay, okay. Well, on that note then, let's proceed on. Incidentally, if I go down to the figure here, is that approximation, that volume of 34, is that approximation an underestimate or an overestimate to the true volume? Good. You can see it. It's an underestimate. That's right. How would we be able to get a better estimate? How could we get a better estimate? Do more rectangles. That's right. That's right. And you know, here they have an example. Well, it's the same problem, same example, but here they're increasing the number of subrectangles. So, like, let me ask you this: in Figure 8, Question A, or Part A, how many subrectangles are there? M equals N equals 4. So, well, does it look like, how many, if you look at the picture there, how many subrectangles is it? Okay, 16. So, okay. What about B? What about B? Okay, 64, because N equals 8. That means 8 times 8 is 64. And finally, C, for C, you have how many subrectangles? 16 squared. Good. And so you can see the volume just gets better and better. Are there any questions about this? Okay, well then let's continue on here. So in example 2, we want to evaluate this double integral. Okay, okay, so now for this problem, when they say evaluate this double integral, are they looking for an approximation? So we are interested in the volume between the surface, square root of 1 minus x squared, and the xy plane over this region R, where x is between -1 and 1, and y is between -2 and 2. When they say double integral here, are we looking for, and that notation here means double integral over the region. Is this double integral, are we talking an approximate volume or the actual volume when you see double integral? It's the actual exact volume. That's right, Ian. That's right. But you've not learned how to do double integrals yet. Okay, you will shortly, but you don't know yet. So for this, you have to use a geometric argument. Okay, so let me ask you this. Let me go to the blackboard for the whiteboard for a minute. For this example 2, z is the square root of 1 minus x squared. What's that look like? What's that look like? Well, in three-dimensional space, I mean, what can I do to help me sort of figure out what this surface looks like? Intuitively, what do you want to do? So, well, let's square both sides. Let's square both sides. So I'll square the z, and I'll square the square root of 1 minus x squared. If we do that, we get z squared equals 1 minus x squared. Or we could think of that as x squared plus z squared equals 1. Now, x squared plus z squared equals 1. What's that an equation of in three-dimensional space? It's a circle in two-dimensional space, but it is indeed a cylinder. That's right, Hunu. It's a cylinder. This is a cylinder. Okay. All right. And you know, all right, that's a cylinder whose central axis is what axis? Good, that's the y-axis. So then, if I go here back to the top, okay, if I go here to the top and this surface here, is this a cylinder? Then is that a full cylinder? It's restricted, right, because this is a plus, right? So, I mean, it has to be what? A blank cylinder. That's a word I'm looking for. Half. Good, Ellie. Good. Good, Hunu. And it's the top half. It's the top half cylinder. So it's half of a cylinder, but the cylinder runs along the y-axis. You know, the y-axis goes through the center of the cylinder, but it's just the top half. Okay. So that being said, let's go then back to the example. Are there any questions? A lot of times when you're given an equation, you can manipulate it, and like I did here, but then you have to look at your restrictions on your original function. All right, well, let's go back to the example then. So here we are. All right, and here I'll show you a picture then. Now they're restricting x to be between -1 and 1, and y to be between 2 and -2. So figure 9, this is what our solid looks like. Are there any questions on that? Okay, can we find the volume of that solid? Can we find this double integral using geometry? I mean, we have half of a cylinder. Do we know how to find the volume of a cylinder? Is there a formula for that? There is. There is. Well, I'll tell you what the formula is. I'll tell you what the formula is. Hold on. Yeah, so the volume of a cylinder is pi times r squared times h. How many recall that? Volume of a cylinder, pi times r squared, that gets you the area of the base of the cylinder, and then times the height. So pi times r squared times h. But our cylinder has a radius of 1, okay, and it has a height of 4. Okay, it's the height of 4. Look at the base. One moment. Sorry, had to turn the phone, had to click on and then off. All right, so here we are. Here we are. I mean, are there any questions that the volume is 2 pi? Are there any questions on what you're seeing there? The only way we got away, the only reason we're able to compute the double integral is because we have a solid that we can find the volume of. If there are no questions, I'll look at one more example with you, and then I'm going to try to give you a little time here to work on section 12.1. Before we move on. Okay, if everybody's good, let's keep going here. Okay, now there's a rule called the midpoint rule. Again, how are you going to select those when, well, like the one example we looked at, in each subrectangle we selected the top right corner. But you don't have to do that. You could select, for instance, the middle of the rectangle, and that's called the midpoint rule for double integrals. Okay, so I mean, I don't even think you really need to I mean, I think it's pretty intuitive, really. But like here in example 3, hold on here one moment. In example 3, they want you to use the midpoint rule with 4 rectangles, because m equals n equals 2, to estimate the value of that double integral. So if we look at the picture, here, here's figure 10. So, and by the way, they tell you that x goes from 0 to 2 and y goes from 1 to 2, right? They tell you that above. So this is our picture. And what would for the subrectangle R11, what's the coordinate? What's the coordinate of that point in the R11 subrectangle? What's the midpoint in the center there? in R11. That's the bottom left subrectangle. A half is right, Ian, for the X. And then 5/4 is correct for the Y. That's right, Juliana. That's right. Hold on, there were a couple of that's right, Ellie. That's right. That's right. Okay. What about R21? What would the midpoint be in that subrectangle? 3/2 and 5/4. That's correct. Good. Good. So, you know, I mean, this isn't rocket science here, although it can be used for rocket science, right? But there is, well, I guess I'll have to highlight it. Won't quite show. I mean, there's how you would compute. You get your approximation for the volume. Now the volume, oh my goodness, the volume's negative, right? The volume's negative. We get negative 11.875. How can we get a negative volume? That's right, Ellie. The function x minus 3y squared must go below the xy plane more than it is. Well, if you were to graph that surface, it would be the net total of volume, the net total of positive volume and negative volume would be negative. Okay, and we'll see something like that. We'll see kind of a nice picture of that later on. But are there any questions on that? Is everybody comfortable with this idea? This kind of introduction? Maybe give me a thumbs up if you're okay. Okay, Juliana's good. Ellie's good. Ian's good. Excellent. Are there any questions? Okay, Malik's good. All right, let me stop the recording.